My name is Greg Moore. I'm a teacher with New South Wales TAFE in Electronics and Communications. This is a wrap-up of what we've done in class in week 2 of amplifiers. And today we'll be talking about BJTs and biasing methods used with those BJTs. So we have a small panel that we'll be using later on in the practical session, and I've drawn already the circuit of that panel up on the whiteboard here. The panel uses a BC109 NPN silicon transistor. Silicon. We've already talked about the differences between silicon and germanium, and even we've talked about some different types of junctions with the Schottky diode too, and in particular the different turn-on characteristics of those 3 different types of materials that are used. With the silicon, we know that with a small signal transistor such as a BC109, we're going to have around about 0.6 of a volt across the base and emitter junction. And that voltage, or that 0.6 of a volt that appears there, is something that we have to overcome when we forward bias that junction. We have to overcome that 0.6 of a volt in order to get current flowing and make the transistor, let's say, work. So if we study this circuit, we've got 12 volts here, we've got a couple of different resistors in series, and ultimately we're going to have some current flowing down here, down through the base to ground. We only need a really tiny current going into the base to make the transistor work, in the order of a few microamps perhaps. And once we get that base emitter junction forward biased and working, then we'll find that we can get a lot of current travelling down through the collector to emitter junction there. So maybe I'll use a different colour for that one and show that we'll have a lot of current travelling down here. Green's a little bit light. Look, maybe the first thing that we need to look at here is the maximum, well, let's consider the 3 different regions for the transistor. Now the transistor can be cut off, that is, there's no current flowing down through the collector emitter at all. The transistor can be saturated, that is, the absolute maximum amount of current can travel down through the collector emitter, and the transistor can be in the active region, which is somewhere between cutoff and saturation. To calculate the saturation value, we've only got, well, we've got to consider that that would become, let's say, a short circuit. If we put enough forward bias into the base circuit, we'll effectively make the junction resistance between the collector and the emitter very, very low. Hence, the only resistance in the circuit is 4.7k. So the only current which is flowing down through here is going to be controlled by the 4.7k resistor and the supply voltage. So capital I, small c, the DC collector current is going to be equal to VCC, I suppose I should have labelled that, the voltage common to the collector rail there, divided by the 4.7k resistor, which is RC. So that'll be 12 divided by 4.7k, 12 divided by 4700 equals 2.55 milliamps. Okay. Now with that 2.55 milliamps, which is saturation current, that's the absolute maximum that we can have travelling down through the collector when the transistor is hard on. So how do we go about making that transistor hard on? We need to consider something else about the transistor. We need to know the beta of the transistor. We need to know the DC current gain of the transistor. And of course, beta is like a quality factor for us here. The beta is going to be the ratio between the base current and the collector current. So if I know what my maximum collector current is, and I know what my beta is, I could divide the collector current by the beta to find out the base current that would be pertinent to that collector current. So what I've done here, I've already got the meter set up with the meter on the beta range, and I've got the test circuit, and I've got a BC108, and I'll bring it a bit closer to the camera there, 278, 279, let's call it 280 is the DC beta of this particular BC109. So that means that we've got a ratio of 280 between the base current and the collector current. So 2.55 milliamps. If I want to find IB equals IC divided by beta equals 2.55 milliamps divided by 280, which would be equal to, by 280, 9.1 microamps. And that would be this current running down here, 9.1 microamps, and that would be the saturation current. But, you know, the problem is with different transistors, even BC109, there's different batches, and the beta, even in one batch, the beta has slight variations. So we can't rely that every BC109 that we looked at has a beta of 280. The beta could range from maybe 180 to 350, who knows? So I've worked with one particular transistor to find the saturation current. And I guess what I'm getting at is, if I put a transistor in a circuit as a replacement, troubleshooting, fault finding, replacement part, and then that replacement part in this circuit has a lower value of beta, 9.1 microamps would not saturate that transistor. So we have to be a little bit careful here in selecting the resistance in the base circuit, that we get a big enough base current that we're always going to saturate that BC109, even if there are tolerances in different BC109 betas. So first of all, how do we work out the base current? Well, the base current is IB, and IB is going to be equal to VBB minus 0.6 volts VBE, because we have to take that away from the 12 volts to get the difference voltage across our RB, so over RB. So in this case it would be 12 minus 0.6 divided by, and this is X, we don't know what that is, but we do know what that is. We know that IB, we wanted 9.1 microamp, but I'm going to allow more current there for the base. I'm going to take this up to 15 microamps to guarantee that we well and truly saturate that transistor. So I'm going to replace that with 15 microamps. 15 microamps equals this divided by X. So how about X, and this will be RB, is going to be equal to 11.4 divided by 15 microamps. 11.4 divided by 11.4 divided by 15 exponent minus 6 equals 760,000 ohms. 760k ohms. 760k, closest that we're going to get to that would be 720k off the shelf. Something that engineers do have to consider, though, is that if this was working off a battery, it's nice, of course, to do what I've done and said, okay, I really want to turn this transistor on hard and make sure it does saturate, if in fact I do want to control a load in the output. But the smaller the resistor I put in the base circuit, the more current that I'm drawing and the faster I'm going to flatten that battery. So, you know, you've got to think about this sometimes and say, is this going to be running off a AC power supply or is it going to be running off battery? And then maybe don't be sort of so fierce with dropping the value of resistances, because it's only a few microamps, but in a larger circuit, a few microamps here, there, a couple of milliamps there, and sooner or later, you know, you've increased your total current demand by maybe 27 milliamps in a battery circuit, and you're going to flatten the battery that much quicker. End of segment 1.